My name is Pranav Munagapati, and this is my Physics 2211 Constant Velocity Lab Report. So, the goals of this lab are to observe an object moving in constant velocity and use the tracker to create an experimental model for the object's motion, create an accurate computer model of the object moving in constant velocity by applying Newton's second law, and compare the two models and explain any similarities or differences. So the concept explored will be Newton's law, which can be seen here in the change in velocity equation, and assuming the net force is 0, this would just boil down to final velocity equals initial velocity. We also use the average velocity equation and the change in position equation. So the procedure is mentioned here, and feel free to pause the video and look over the procedure, but this is pretty much the same thing I explained in the goals of the video. So this right here is my experimental data, and as you can see, I'm rolling a cylindrical water bottle, so with a uniform, it's a uniform shape across a flat surface, so it should have constant velocity. And in the bottom right are all the data points I collected from this, so the time and the position and a position time graph. And as you can see here, when these points are plotted, you see a negative slope in the position time graph, and the y-axis is position along the x-axis, and the x-axis is time. And then I use that data to calculate the slope and use that as my velocity in the computational model. So as you can see, I plugged in that velocity in the computational model here and here. And I actually had two different computational models using two different slopes. So the first one was the computational model I found using just the initial velocity. So I used the first frame at t equals 0.0167 seconds, and I compared that to the time at rest, and I found the velocity of that and found it to be negative 0.27 meters per second. And then I used the average velocity across the entire data set, so from t equals 3.303 seconds till rest, and found the velocity of that to be higher at negative 0.342 meters per second. So this is the graph using the initial velocity of both the experimental and theoretical position in time, and this is the one using the average velocity model. So as you can see, there's a much tighter spread for the average velocity model, and there's less discrepancy in the data. And so for that reason, I decided to go with the average velocity model, and I believe this is because it accounts for more data across the entire experiment, which leads to less chance of error, since the first graph could still account for any initial acceleration present at that time, or any bumps on the surface of the table or anything. And this average velocity model has a larger data sample, so therefore it automatically has less chance of error. So as you can see by this graph, the experimental and computational model are almost identical, which leads me to the conclusion that the experimental model is almost at constant velocity, which means there should be no net force. And as you can see, they both start with the same velocity, since they're pretty much on top of the lines on top of each other. But then the experimental one decelerates as the theoretical is still continuing. And I believe this is due to the force of friction that the table is applying on the water bottle in the opposite direction of motion. So I feel like because of that, the water bottle is decelerating. But then as you can see, it picks back up and matches back up to the line of the theoretical one, which is the computational model. And I feel like this is due to the force of gravity, because when I went back to examine why this happened, I noticed that the table was slanted in the direction the water bottle was moving. So gravity would be speeding the water bottle up or accelerating it. So that's another net force. So that's adding a net force in the direction of movement, which is why it's speeding back up. And so it's overcoming the force of friction, and it's accelerating back up to meet back up with this theoretical line. And so my source of error, I said, or as I mentioned already, the friction of the surface and the slanted surface, but also the acceleration from my hand when I released the water bottle. When I was analyzing the time, the water bottle could have still been accelerating at the time I was looking at it. So I didn't account for that. And the water bottle could be rolling in other directions, such as the y and z planes, not only the x plane. And then finally, in the track graph itself, I could have been incorrectly labeling the point of mass, which would have messed up my data. So if I had to change the positive and negative axes and interchange them, I feel like the results of the lab would not change. All this would indicate is that the object is traveling in the opposite direction. So instead of right to left, it'd be going left to right. The magnitude of the force and velocity would remain the exact same, so the findings are no different. And then, is it possible for me to say how many pushes and pulls are added together to give a zero net force? In the case of my object, I think it is possible to count the number of forces acting on the object. There's the initial force of my hand rolling the bottle, the force of friction in the opposite direction of motion, and the force of gravity due to the slant in the table. Theoretically, the force of my hand and the gravity should be equal to the force of friction to have a net force of 0, but as we can see in the graph, there's decelerations and accelerations, meaning there is a non-zero net force at times. So one of the three is outweighing each other.